Here are a couple questions relating to pressure and buoyancy. First question says that we have a full-term fetus that typically has a mass of 3.5 kilograms. It asks us, what pressure does that fetus create on the mother's bladder? And it gives us the area for maybe the top of the bladder. So we can draw this. Maybe I'll draw a baby. Kind of like this. Maybe the baby's happy. Okay, and we can draw a bladder. Maybe it looks like that. Okay. So we're given the mass of the baby, and the mass relates to this force that the baby is applying to the bladder. Okay, so the force is simply mg. And we're told that the area here, the area of the top, is 90 square centimeters. Okay, so if we're going to do anything in some kind of an equation, to get the units we expect to get, we need to convert this to SI. So the SI unit for area is square meters. So I need to move this by a factor of 100. So I need to divide by 100, and I need to do it twice. Okay, so I move 4 places to the left, I end up with 0.009 square meters. Okay, so to answer question A, I'm asking what is the pressure? So pressure is simply the force spread over some area, right? Force over area. The force again is mg, and area is something I have. So let me plug in the numbers here. It's 3.5 kilograms times 9.8 meters per second squared divided by 0.009 square meters. And if you do this, you end up with 3,811 newtons per square meter. All right, or you get, what is that, kilogram meters per second squared divided by meters squared, right? And a kilogram meters per second squared is a newton. And just to throw a third unit in here, we can round this down to 3,800, and that's in pascals. Right? Again, pascals or newtons per square meter, those are both acceptable. Those are both the SI unit. Because you notice it doesn't change the number, right? Pascal is defined as a newton per square meter. So the second part of this question informs us that pressures inside a bladder typically range from 0 to 25 millimeters of mercury. So millimeters of mercury, that is another unit for pressure. Okay, when the pressure reaches the upper end of this range, there's a reflex in your body that tells you that your bladder is full. Right? So the question is this pressure created simply by the fetus on a bladder, is that enough to trigger this reflex? So question B is simply asking, how does 3,800 pascals compare to the upper end of this range? So I could say to 25 millimeters of mercury. Alright, so in order to answer that question, I need to know what is 3,800 pascals in millimeters of mercury. Or I could convert 25 millimeters of mercury to 3,800. I'm going to do the former in this case. Okay, so I need the conversion factor, and it turns out that 101,300 pascals is equal to 760 millimeters of mercury. Alright, and in fact, those are both equal to 1 atmosphere. Alright? So this much of this this equality is my conversion factor. Okay, so I start with my answer for part A, and I'm going to leave the 11 on it just so that I'm not rounding prematurely. So 3,811 pascals times this conversion factor, so I want pascals to go away and millimeters of mercury to show up. So that's 760 upstairs, 101,300 downstairs, and if you do this math, you end up with 28.6 millimeters of mercury. So, yes, the fetus will indeed trigger the reflex. Right, that's just above the range, so certainly will trigger that reflex. So the second question here is it's related to buoyancy. Okay, so we're told that if the body has a density of 995 kilograms per cubic meter, what fraction will be submerged when floating gently in freshwater and salt water? And they give us the density for salt water. Okay, so you should be able to imagine this. Let's draw a picture. Here's a person, and they're floating gently in some fluid, so there. So we can identify part of this person is submerged and part of the person is not, right? So what we'd like to compare is the portion that's submerged to the entire entirety of the body. So what will make sense here is to talk about volumes. So this is volume submerged, and this is total volume. Okay, since we're asking for what fraction is submerged, what we're asked to find here is the ratio of these two things, V sub over V total. All right, this is what we're looking for, this fraction. Okay, so a simple thing we can do here is to draw a free body diagram for the person. Free body diagram. And we can label some forces on this diagram. Clearly there's gravity acting, so we'll draw a line down and just call that mg for mass of the body times g. And instead of thinking of pressures, we're going to think of buoyant force, so F sub B. And to some extent there is air pushing down on the body from above, but that's a very small force compared to the two forces that are acting here, so we're going to ignore it. So buoyant force here, we should recall that buoyant force is equal to the density of the fluid, right? So density of the water or the salt water times G times V displaced. Okay? And V displaced in this case is equal to the volume submerged. Right? So this is Archimedes' principle, just saying that when an object displaces a fluid, it feels the force that the fluid it displaced was feeling. Right? So now we can apply Newton's second law here. We'll say the sum of the forces in the y direction equals 0 in this case because we're floating gently. Alright, so evidently we're not moving up or down, so there's no net force. So that means that the buoyant force minus weight equals 0. So at this point, it is convenient to notice that we can represent the weight of the person, or at least part of this expression, the mass of the person, as we'll see here. The mass of the body is the density of the body times the total volume. All right, and that's good because what we're looking for has total volume in it. Okay, so we'll move mg to the other side and replace m with this expression, this density of the body times the total volume. And in the same step, we'll replace the buoyant force with this expression. So I'll write rho fluid times g times v displaced equals rho body times g times v total. Okay, so the g's divide out, and it looks like the fraction I'm looking for can be obtained just by dividing v total to this side and rho fluid to that side. So v displaced divided by v total equals rho body divided by rho fluid. Okay, so now I'm ready to plug in some numbers. Let me highlight that a little further. So for part A, v displaced over v total is, again, rho body over rho fluid, so it's 995 kilograms per cubic meter divided by the density of fresh water, which is 1,000 kilograms per cubic meter. All right, and what I get for that one, it looks like I just need to move the decimal a few places, 0.995. All right, so that's the fraction, or the part of 100, right? This 0.995 of the body is submerged in fresh water, so that's quite a bit of it. Let's compare that to salt water. For salt water, v displaced over v total looks like it should be, again, this 995 kilograms per cubic meter. And now the density is 1,027 for salt water. All right, and when you do that math, you end up with 0.969. So a fair bit more is exposed. So now you can see maybe why objects might be more likely to float in salt water than fresh water.